Greetings, everyone. This is my November 8th, 2010 ENE 350 lecture, and I'm going to talk about interrupts. An interrupt is a request that one device makes to another device to receive attention. Typically, the requesting device needs service from another device that is capable of providing such a service. In our context, keyboards, printers, scanners, touchpads, and other devices such as a power management unit request service from a processor such as VESP. Pictorially, we can view the process of interrupt as an action that takes place between a central processing unit such as our VESP and a set of devices such as these four devices in this example. A device, when it wants to receive a service, requests that service from the processor and in return receives an acknowledgement in case that service is providable to that device. And this can happen between any of the devices and the central processor unit. And of course, we have to factor into this the priority that must be established between these devices in the event that you have several devices requesting service all at once. So on the next slide, I am just going to reiterate that we need a mechanism to select the device for service in the event that more than one device interrupts our processor for service. And such a mechanism is often implemented by what I call an interrupt priority encoder. Now, an 8-input priority encoder is shown in this slide, where we have some 8 devices labeled from D0 to D7. Enter an 8 to 3 priority encoder in order to receive a service based on the priority that they have, or the priorities they have, and what other devices make similar requests. So the priority of D0 is the lowest priority in this scheme, and that is equal to 0, or 000 in binary. And the priority of device D7 is the highest priority among all the devices, or their priorities, and it's given the priority of 7, or 111 in binary. So when a number of these devices make a request, as in this example, D2, D5, and D6, the one with the highest priority, which is in this case D6, receives the request or service that it requests. In this case, these 1 entries in these device positions result in a device ID of 110, simply matching the ID or the priority of the device that has the highest priority among all the devices that made a request for service. Now, in this situation, since device D7 has not made any request, D6, having made a request, such a request, does receive the service because the other 2 devices that make a similar request have lower priority. Now, in this truth table, we depict or describe how these devices, or the requests that these devices make, the 8 devices we saw in the earlier slide, how their various combinations lead to the device ID representation, or the combination for these different cases. So in the event that device D7 makes a request, then the device ID is equal to 111, regardless of what the other devices request service, whether or not, rather, the other devices make such a request. In the event that the highest most priority device, that is D7, does not make such a service request, but D6 does, then regardless of all the remaining devices, D5 through D0, whatever their request status are, the device ID resolves itself to 110 because it is device D6 that makes such a request when device D7 does not. And you can pretty much follow this logic all the way to the end, where you could see that when device D7, D6, D5, D4, D3, D2 do not make a request for service, but D1 does, then the request is granted to that device D1, and that's actually designated as device ID 001. In fact, there's one more combination that I have to mention, and that is when the last device here, which is D0, makes a request, and all the other devices with higher priority, namely D1 through D7, do not make any such request, then it is actually device ID 000 that is assigned to these three binary variables. Now, there's one other combination that we have to pay attention to, and that is when none of the devices makes a request. And as you can see, that can really happen. And the way we differentiate that, or enter that as the next, or as the ninth choice, is by way of this extra variable, which I would simply say the request status variable, which is clear to 0, just to indicate that there's no request that is made. So we can say that that request output or signal is equal to 1, as it is stated here, if at least one of the devices makes a request or interrupts the processor, and 0 otherwise. And you can simply see from the logical combinations that these devices assume. All we have to do is to require that one of these devices make such a request, and that would simply be D7 or D6 or D5 all the way to D0. And with this sort of a truth table, we could easily write out formulas for the three binary variables, y2, y1, and y0, simply by resolving the output values of 1 for each of the three variables to the associated combination. For example, y2 is 1 if d7 is 1, and it doesn't matter what the others are. And that's just one of 4 possibilities for y2 to be 1. And another possibility is d7 is 0 and d6 is 1, which is to say d7 does not make a request for interrupt service, but d6 does, and doesn't matter what the other ones do. And that's another possibility or a combination for y2 to assume a value of 1. And the other 2 cases are right up here. And so all we do, we take either d7, as you will see down here, d7, or d7 not d6, which is this one, or that vertical bar simply represents or as in C programming language, or d7 not, d6 not, and d5, as you can see that's the case here. And finally, it could be d7 not, d6 not, d5 not, and d4. And if you actually simplify this, it resolves, or it reduces to d7 or d6 or d5 or d4. Those are the variables that are all together to generate the output. For output y2, the values of 1. In all of the cases, we will have a 0. And so with this, you then have clearly Boolean circuits or switching circuits with which you could code all the three binary variables which collectively make up your these three binary variables that collectively make up the device ID, and this is really your priority encoder, which gives you the capability to identify in the presence of multitude of requests which device receives the service by our CPU. Now, it is possible when requests are made that devices need different services. Different devices may require different services. A printer's needs will be different than a keyboard's needs, and that's obvious. So because such a thing exists, we would like to think of these services as computer programs that accomplish whatever the nature of the request or the service that is requested is. So we would generally refer to such services as interrupt routines. And interrupt routines are really computer programs which could either be written in a high-level language such as C or C++ or even Java, or they could be machine language expressed programs, assembly language programs, as in the case of VESP. So we could safely say that an interrupt routine is a computer program, or a VESP program in our case, that is executed when a device makes a request, and that device is granted the service that it requested. Interrupt routines are stored in the core memory of a computer and form an integral part of the system architecture of the computer. You can almost think of them as part of the kernel of a computer, where these interrupt routines are pulled from wherever they're located in the core memory for execution within the vicinity of the CPU. Now, interrupts can really come in a number of shapes or forms or types, and I would like to emphasize that there are at least, operationally speaking, two types of interrupts. I call them single-level interrupts, in which case the CPU cannot be interrupted while servicing a device, or they could be recursive or nested interrupts, where CPU can be interrupted by another device while servicing a given device. Now, in this lecture, I'm only going to focus on single-level interrupts, as the recursive or the nested interrupts will take a little more effort to understand, and we need to get through this single-level interrupt concept just to really get ourselves soaked in this idea of how a processor deals with an interrupt request. We need to sort of integrate that right into our VESP structure, as you will see that will happen in the next slide or two. And once we get that taken care of, we can then talk about how we deal with the issue of recursive or nested interrupts, which is a lot more exciting and interesting than a single-level interrupts. But as I said, you really need to know what an interrupt process entails as it is seen from a CPU point of view. So when I'm thinking about a single-level interrupt, I am primarily thinking about modifying the basic fetch, decode, execute loop that we've learned in the very early going when we first started to cover subjects in ENEE350. So to us, a processor was something that fetched an instruction, decoded it, and executed it. And then that whole process was repeated over and over again until we saw an instruction that said halt or stop execution. That's what this loop is over here would have been. Now, with the addition of an interrupt capability to a processor, we need to put that capability right into that loop where the processor constantly repeats this process of fetch, decode, execute cycle. And so at the beginning of each cycle, or we can change this, as you will see in the case of VESP, every so many cycles, clock cycles, we could force the processor or our VESP to examine a set of flags, or some maybe single flag, just to determine if a request for an interrupt request has been made for service. And if so, then VESP can go out and perform that service by way of executing a program which we call an interrupt routine. And then once that is concluded, VESP can then return to the next step, which will be to go and fetch the next instruction, decode it, and execute it. And this can go on, as in the typical loop of a processor, from fetch to execution. And all we did in this situation is to add or insert that one extra step, which in this example will be repeated every clock cycle. Not every clock cycle, every instruction cycle, or machine cycle, because obviously we'll take some clock cycles just doing these steps, and I really mean machine cycles, so I want to stand corrected on that. Okay, and that's just added, and you can see that the overhead would be about 20% here. Just doing this one step, but in reality will be more than 20%, because when we go out and do an interrupt request service, we provide service for that, we're going to end up executing a whole bunch of instructions. So it's going to be more than just looking at a request flag, an interrupt request flag, to see if an interrupt has been requested. So that just has to be kept in mind, and that will decide how frequently we want to give the interrupt request a priority, or I guess you could say the capability to interrupt the machine. As you'll see in the next slide or two, we will allow VESP to interrupt itself, if you like, every 5 clock cycles, and that way we get to do what VESP needs to do for let's say clock cycles. At the end of that, during the 5th cycle, it can actually go out and pick an instruction from a interrupt routine and then execute it all the way to the end. Now, in some cases, like a power management unit situation, where a request comes from such a device for a, I guess you could say, a significant failure, like power may run out, or other things may happen. In that situation, of course, the priority has to be kept at a maximum. So we could elaborate a little more about what really goes on when we say that we want to service a device that has made a request for interrupt. So what we do is we go out and check a device has requested service, after which we identify the device with the highest priority, and then we service it, and then we go and fall into the first 3 steps, or the original 3 steps in a typical fetch, decode, execute cycle of a computer. So, and we saw how, if I go back a slide here, we saw how this identification is done, and that was done via this capability here, this sort of a priority encoder. So we could use a circuit like that just to get that taken care of. Now, the service itself, as I said, is really nothing but another VESP program in our example, another computer program that must be executed from beginning to end in the case of a single level interrupt. And once that is over, then the computer can go and execute the next instruction that it had suspended just to handle this request that was made. Now, our VESP architecture for this, and of course we've been doing these VESP machines in C++, goes by the name of VESP30I, I for interrupt. And this particular sort of version is designed to handle up to 8 peripheral devices in a single level service request handling way. The interrupt routines, the actual programs, are stored in hexadecimal location 100, 140, 180, 1C0, 200, 240, 280, and 2C0. You can see that each of the interrupt routines in decimal terms will take 64 locations to be fitted into. And of course, that means less, at most 64 instructions, because we know that in VESP some instructions take more than one location. So, but we can safely say that each routine is a VESP program that is limited to 64 memory locations, which will mean that 64 or less, or at most 64 VESP instructions that we can execute within each of these so-called interrupt service routines. Now, one of the things that we shall see will happen while we're designing an interrupt scheme for VESP is that we will introduce 2 instructions, one of which is actually going to play a more of a critical role in this case. And these 2 instructions, called JTI, jump to subroutine, jump to interrupt rather, and RTI, return from an interrupt, will facilitate our interrupt servicing processes. In other words, we will be able to initiate and terminate interrupt routines by way of inserting these 2 instructions, JTI and RTI, at the beginning and at the end of such a routine. Now, as I said, it is more, or the RTI instruction plays a more critical role in the case of a single level interrupt handling. And all we have to do is to insert such an instruction at the end of each service routine so that when that happens, the VESP machine knows where to return to pick up the next instruction it had left off when it first began to service the request. And so you can say that the execution of the RTI instruction restores the PC to the saved address of the next instruction to be executed after the interrupt service is completed, and then sets the RTI flag to 1 to force VESP to return to the main loop. In other words, to exit out of the interrupt loop, or the interrupt service routine loop, which it had been executing all along until it encounters that RTI instruction. With those 2 things happening, then VESP knows that it first of all has to end the routine, and second of all, it actually knows where to go back to, because RTI instruction does make such a recording of the instruction that we had left behind as we entered the execution of this particular sort of routine that we're executing. Now, as I said, we tap these routines, so-called interrupt service routines, by these locations. Now, since they are all separated by 64 decimal locations from one another, all we have to do is know, this would be to know that a given routine has a device ID associated with it. For example, we just have to displace the initial location of 0100 by that multiple of 64, which is given by the ID of the device that requests service and has won the priority game, if you like. So, for example, if no other device makes a request but device 0 does, we go to location 100. If on the other hand, it is the first device that made a request, and whether that actually first, when I say first, it is like device 1, then we clearly, and no other device past device, let's say 1, not device 0, makes a request for service, then of course we go to location 10. That's just 64 locations apart from this place. And if it were to be device number 2, that would be 2 times 64. So you can see it's like, 100 plus the number, the ID of the routine, the device rather, that makes that request times 64 will give us the starting location of the service routine. So if I make myself, for example, if as VESP, if I decide to serve device number 2, then I would simply say that device's interrupt service routine is located in 100 plus 2 times 64, or 2 times 40 in hexadecimal, which would be 180. If it were to be 3 times, that would be device number, not 0, not 1, not 2, but 3, and that would be 4 times, again, 40 in hexadecimal, or 64 in decimal, plus that initial place. So there's a displacement process which very precisely provides us the very location of the first instruction in the service routine that is specifically designed for that device for its service. Now, so here is the so-called serve device function, which puts all of these concepts into specific form. The messages that you read here are not really as critical. They're just letting us what device is being served, and that would be provided to this program by a global variable in this situation. And that same device served ID, the ID of that device that is being served, will be, as I just mentioned in the earlier slide, will be multiplied by hexadecimal 40 and added to 0100 to determine the location of the first instruction in that service routine, interrupt service routine, that was matched to that interrupting device. And so that the program counter value is then used to initiate the process of execution. And as you can see, that we do have this so-called RTI flag, which is initialized to 0, and we're going to keep executing this main cycle, which will continue to execute, I should say, as long as there's no halt instruction and there is no return from interrupt instruction, which upon execution would actually set VESP RTI to 1, and that will be sufficient to break this cycle. So as I wrote down here, the while loop here is terminated if either a halt or an RTI instruction is executed. Now you may just say, well, we just clear it to 0, and how is it possible for this to be ever 1? As I just said, every one of these interrupt service routines happens to end with an RTI instruction whose job is to set this vesp.rti to 1. And when that happens, this whole loop then ceases to exist, and therefore we come out of this loop. And of course, this is the C version or C++ version of that priority encoder that I explained to you earlier. As you can see, the highest priority is given to the interrupt device, or the device number 7, and if that device happens to have a request made, then all we have to do is to say the device that's made the request is equal to 7 and break. This is really the encoding process, which I have converted into a C++ code, and I know that if that device is device number 7, I'm just going to say the service must be given to device number 7, and that is what this is basically stating here. If it is 0, in other words, if that bit flag is not equal to 1, that is, it's equal to 0, then I'm going to have to interrogate what happens to, or what actually, whether or not device number 6 makes a request, and that is this case. And again, in this case, if that is equal to 1, then we actually go, and I think it seems like I made a tiny bit of an error here, because I'm looking to see that in the switch statement itself I just wrote something excessive. Let me quickly correct that. All I wanted to do here was just to make this test, and that should take care of it right there. Again, if that's equal to 1, then I'm going to sort of say that my device is now device 6. If not, then I'm going to have to check device 5 and then do the same for it. If it's not, I go check device 4. So you can see that in decreasing priority, I reach all the way to device 0. If none of them actually did request, then I come out without setting VESP device served to any of these values. So effectively, you can say this function minus that request status bit does implement the 8 input priority encoder that we talked about earlier. So with these two functions in place, that is to say, which device to serve and what to do when the service comes, they just constitute the main extensions to our VESP architecture. These two functions have to be part of our VESP now in order for us to handle interrupts, in the case of single level interrupts, of course. Now, the only other thing that's really left to talk about here is how to modify the main execution loop of VESP. Now, we're talking about specific things that pertain to VESP and VESP's fetch, decode, execute process. And as you recall, in the simplest architecture we saw of VESP, we were simply checking to see if a halt instruction was executed, or somehow a request for reset comes about as one of the action choices we may have. We then terminate the loop. When we don't terminate the loop, we could actually do either a step, which is this case 1, we do one main cycle and then simply break, or we can go into a repetitive execution of the main cycle, which will be only terminated, when we encounter a halt instruction. So I would say, we will simply start our loop and figure out what action we need to take, and those are the 3 actions. And this is the basic VESP execution loop without the interrupt process incorporated into it. So now we have to put that in, which is to say we need to get somehow some modification inserted into this process so that our loop allows us to do an interrupt service. Now, how would we go about doing that? We would go about doing that by simply picking which device to serve, which is really given by this process. And that means we have something called VESP interrupt vector, which has to be updated every time or just before we look at it. And then once we know what device to service, we then go out here and then set the program counter to that device's interrupt service routine location, which is like 100 plus 40, or hexadecimal 40 times the device ID, and then start executing until an RTI or a halt instruction is invoked. So with all that, let's see how this really takes shape right up here. Now this is more or less the complete picture. I'm going to simplify this in the next slide so you can see how the big picture sort of appears. But if you look at this, you have a lot of detail here, which I think you may not necessarily enjoy sort of going through the first round. But this is the simpler of the two cases, so you better get this totally understood, between this presentation I'm giving here and and maybe actually firing up the code and seeing what is transpiring. But the main loop we talked about in this simplest case, or in one of the simpler cases, still is here. As you can see, we still want to do an infinite loop, or a loop until we don't break until the reset becomes 0. And then we have choices here. Either we could execute the program, or step it, or we can exit to the main menu. And all of that is just selected or activated by writing something into this action variable, which then kicks into the switch statement. And with that action 2, we now have 3 choices. Case 0, which is really the process of execution indefinitely until we either encounter a halt instruction, or as we see, an interrupt, return from interrupt instruction. And the second case is the step function, which we were doing earlier. And the third case is just do a hard reset, which is to say that when we in fact pick that action 2, we get to action 2 to be equal to 2, we then make this choice. Now, as you can see, that this is going to repeat all the time, and of course that repetition is going to give us the ability to effectively incorporate now our interrupt routine into this space. Now, as you can see, that we do have this infinite loop, which we will not be able to break out of, even in the presence of an action of 2 here, because we have a second loop which forces us to remain within the loop without ever going through this external loop, as long as we don't see a halt instruction. That's in fact without putting the interrupt capability. And just to refresh our thoughts again, now watch. Case 0 was our execute cycle. Case 1 was our step cycle, and case 2 was our basically bail out and break this external loop option. Now those 3 options are here, 0, 1, 2. The only thing that I will now change, or we will now change, is this while loop will not just do the main cycle with the action that we will perform. This action is also something that's actually initialized prior to this step, so that should not be confused with this action 2. That's actually entered earlier on. Now, if I go over here, you will see that I'm not only doing the main cycle here, but I'm doing something more than that. And exactly what I am doing, it is defined here. It says, if j is mod 5 is equal to 0. Now, I just want to remind you, and you'll see this when you look at the interrupt version of VESP, that code, that j was the number of instructions executed until this point where we are now looking at this value of j. So initially we have no instructions executed. We have then 1 instruction executed, 2 instructions, 3 instructions. So that value of j is actually incremented every time we do a main cycle. So all we're saying is that when we find this to be a multiple of 5, like it could be 5, it could be 10, 15, and so on. That's how this turns out to be 0. Remainder of j divided by 5 will be 0 when it's 5, 10, and so on. And I guess I start j at 1 so that we never really encounter the case where this is equal to 0 when j is equal to 0, because that never happens. So when that happens, I would like to interrupt. So all that is saying is that I'd like to interrupt every 5 instructions or so. I don't want to interrupt VESP any more frequently than this because I don't want VESP to be bogged down or drained by the interrupt routines that it may have to serve. So this gives VESP the capability to execute a bunch of instructions, some 5 instructions, and then go ahead and do this. So now when an interrupt routine request is made, we have to detect this. So we really do this by going through this fairly detailed code, which I will only mention at a given level of detail so that you don't get confused about this anymore than you have to. And what you are seeing over here is that we are actually keeping track of what devices are going to interrupt when we look at these interrupt values or interrupt request values. So that is all stored in this place called VESP memory I, and I begins at location 4. That's our good old core memory, by the way. And you can see that we store these requests for interrupt, which are really ones and zeros, in locations 4 through B, and there will be precisely 8 such locations. And what we do is then we keep reading, and the reason that we actually have 2 get chars is because one of them is a return, sort of like a carried return value. And then with these things stored, we can now go ahead and determine if, for example, down here, a request has been made, and this will happen if any one of these interrupt vectors, vector values, the so-called the interrupt vector I, happens to be 1. And that will be enough to make the interrupt request to turn 1 here. And once that turns 1, then we go ahead and save our accumulator, our B accumulator, if you like, or B register and IX register. Those are the 3 that we definitely save. And we go ahead and save them into locations 1A, 1B, and 1C because we want to save those just because we actually may have left in them some operands that should not be destroyed simply because we go out and execute some service routine. Now, after which we also save the program counter to what I call the saved PC register or a location. And then I go out and do the priority encoder to figure out exactly which of the devices has made an interrupt, and then I do a serve device. That is to say, go out now, execute that particular sort of program that is required to provide the service for that device. Once that is over, restore the 3 registers we saved, so-called the accumulator, the B register, and the index register, and then set the interrupt flag to 0 so that we could do this again. As you can see, all of this is going to happen until we are done with the service. After which, we then proceed on to the execution of the instruction we had suspended by way of this main cycle that was to execute if we had not gone into this loop. So with that, really this is the only change we made, and the other things didn't change because those are not where we make this kind of an insertion. And this is where the interrupt routine is processed or executed for the device that is serviced. Now, a more compact version of this is right here, where I really simplified all that, I guess you can say, excessive and very detailed explanation, which is really what the code itself is, by writing some things up instead of those. I said, for example, reset the interrupt vector, read in the interrupts, clear the interrupt flag, and set the interrupt flag in case that one of the devices made a request. And if you find at the end of that process, in other words, once you computed VESP interrupt the flag and find that to be equal to 1, go ahead, save A, B, and IX and save PC. And I'm not really, except for PC, I'm not showing how you save A, B, and IX, which I have shown in the earlier slide. Go ahead and do priority encoding, do the serve device function. Once you finish with that, Then you, let me just go back to this, I guess my inadvertently switch back to that slide. Then just clear the interrupt bit and then go back. Do the main cycle, and the next time you will visit this area would be when J becomes 10. So you can see that every 5 instructions I check to see if there is a request that VESP must handle. If there is, then I go out and handle it. Now you can, if this is too frequent to do, I may just simply do this every 10 clock cycles or every 10 machine cycles so that I don't really get to slow down my processor unnecessarily. That's just something that I, as an architect of this engine, can decide based on the performance of the machine that I'm watching. So we need to talk a little bit about the interrupt routines themselves, and you all know by now, hopefully, that these routines will be stored in very specific locations. The first one will be located at 100 and will go 64 locations from that on to 140. And then after that, we'll start the next interrupt routine, and we'll go all the way up to 180. And then we will go another 40 or 64 locations, and then we'll go to 1C0. And it'll go on all the way up to the very last routine. So those are where our routines are. So when we're actually diverging to execute here, let's say, some service, and that service is being, or is picked up from that location, which is computed by the ID of the device served times 40 plus this hexadecimal 100. That's where the program is. So we're not really doing anything unusual when we realize that there is a service to be provided. We just want to know which device has won the service request. We then find the first instruction where that a service routine will be located for that very device that is actually now going to be served, and then we go and execute it. This is just another, as you can see, main cycle. That's another execution process which will continue until a halt instruction or a RTI instruction, which is to say return from the interrupt instruction, is encountered. So with all that, we're really sort of like, we just have to look at the fact that these are programs, the interrupt routines, service routines, or as sometimes they call vectors, are those programs that are stored in those locations, the locations starting at hexadecimal 100 and then proceeding on in chunks of 64 locations. And if you were to do more than 8 devices, then you have to make some core memory allocations, new allocations for those new services that you want to provide. It's of course always possible that your devices may not really have new requests or new services, but you may have more than 8 devices. That's all possible. In that case, you maintain your memory allocation, and you still have only 8 services to provide, but you have more devices, some of which will have the same service provided. So you can have 2 printers of the very same make, and that means that your services will be identical. There may be some minute changes, but they will not require an entire region or a set of locations for a service routine. So I could summarize what we really learned in this very class or lecture. We learned what an interrupt is, hopefully, and how it is handled by a processor. We learned how VESP handles single-level interrupts, and that was to say that, or that is to say that, in case that a device comes in to make a request for an interrupt, we don't really allow that to happen, to proceed, until everything that we're executing for that device that is currently serviced is over. Now, the way that you see that is by looking at this. So we do go to the serve device function and go out and finish that service, and then only after that we just set this interrupt flag to 0. And then we have to recalculate some 5 machine cycles later if we have another request. Now, one disadvantage of this process is that if, let's say, a higher priority device constantly keeps interrupting a lower priority one, will never get a chance to actually get served. Let's say that every time that I look at this interrupt request vector, I see serve. Let's say that device 7 makes a request every single time. Device 6, 5, 4, 3, 2, 1, 0. None of them will have any chance to get ever serviced. So one of the ways to avoid this, or to rectify or ease this situation, is to allow ourselves to make recursive interrupts, where an interrupted or a service that is being provided to a device that has just interrupted the CPU can actually be interrupted by another device of lower priority once we are certain that that higher priority device is actually being served, and we will return to it at a later time. Of course, there also you have to be careful, because you don't want to have a lower priority device to constantly keep taking the time away from a higher priority device. And so those things I think I'm going to talk about when we reconvene our class on location on Wednesday. What I would urge you to do once you get this set of slides, please do take the time to go over my discussion today and bring up any questions you may have to class on Wednesday, and then we can go over those. And so my plan is then to cover recursive interrupts on Wednesday, but maybe before then, in case that you have any questions, I may spend a little bit of time on the single level interrupt process, which we have gone into some details of in this lecture. So with all of this said, I look forward to seeing everybody on Wednesday back in College Park. Until then, take care.